Welcome to Mastering Solutions. Let's start off by making a list of all the information that they give us in this problem. And they tell us that we have the thickness of the coating in this case, so that's T, and that's going to be 90 nanometers, 10 to the negative 9 meters. And then we are told that we have the wavelength, so lambda is going to be 480 nanometers. We'll get to the M here in just a second. And then let's draw a picture so we can see how many phase changes we have in this. So in this case, I don't like the way this question's worded. I think it's kind of confusing, but what they're trying to say is they're trying to go from a high to low index of refraction. So this first one right here is the material for the glasses. Most glasses anymore are not actually made of glass. They're made out of different polymers like polycarbonate or other things like that. But they say in the problem that assume the coating's index of refraction is less than that of the lens. So this one is higher. And then here we have our thin film on the inside of the glasses. And that they say is 1.38. So this one up here doesn't really matter what it is, but it's more than 1.38. And then down here we have N of 1 for the air. And this is the N. So now when we draw our light coming through here, we're going to have the light come through the glass, and it's going from a higher to a lower like we talked about. And so there will be no phase change here. I'll go like that. And then the light, of course, is going to get reflected. And then here, it's also going to get reflected. Okay, so this is what the light's going to do. And because we're constantly going from higher to lower indices of refraction, we don't have any phase changes here. And because we are looking for an anti-reflective coating, we are looking for destructive interference. For zero phase changes and for destructive interference, the equation is going to be equal to m plus 1/2 because of the destructive interference. And then we're going to have lambda over n. Now going back to m, because we're dealing with destructive interference, we're not going to use 1, we're actually going to use 0 for the thinnest possible coating. And now for part A, what is it that we need to find here? What must be the coating's index of refraction to be effective at this? Okay, sorry, so I read the question wrong. So this is for part B, so let's just ignore this for now. So for the first part, we don't know what the N is, and that's what we're trying to solve for. And that's why they say here that assume that the index of refraction is from high to low, from the glasses down through the coating into the air. And so now we need to do some math here to solve this equation for N. For my brain, it works a little bit easier if we rewrite the equation like this. 2t is equal to m plus 1/2 times lambda over n. Now we can multiply both sides of the equation by n, and then we'll divide back over the 2t. So that will leave us with n is equal to m plus 1/2 times lambda over 2t. Even though it's fine to plug in all the information here, we can simplify it a step further. We know that m is 0, so that's going to be 1/2 lambda over 2t. But if we multiply the top and the bottom by 2, that will give us lambda over 4t. So this is our simplified equation to solve for n. And so now we just need to plug these two in. So lambda is 480 times 10 to the negative 9 meters, and that's divided by 4 times the thickness, which we said is 90 microns, 90 times 10 to the negative 9. Okay. So now we have 480 times 10 to the negative 9, and that's divided by 4 times 90 times 10 to the negative 9. So for the index of refraction for part A, like I said, ignoring that for part B. So for part A, the answer is going to be index of refraction of 1.33 for the thin film coating. Now we can move on to part B when they say if the index of refraction is 1.38, now we need to figure out what the thickness is. And so just like we did above, we can use the same equation Let's put B here. Okay, so 2t is equal to m plus 1/2 times lambda over n. And we need to solve it for t. So this one, all we have to do is multiply both sides by 2. And it's going to be the same thing. This is 0. So now we're left with t is equal to lambda over 4n. And as we talked about, we're using m of 0 for the thinnest possible coating because we're using destructive interference. And so we have 480 times 10 to the negative 9 meters divided by 4 times the n, and they said is 1.38. So we have 480 times 10 to the negative 9 divided by 4 times 1.38. Not 9, 8. And we get a 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 87 nanometers is the answer for the thinnest possible coating for part B.